Thank you very much, Bernat and Oriol, for the invitation. So today I will be talking indeed about the project, the ERC project that we are currently undertaking, which is about how we can model the acoustic footprint underneath the water in offshore environments when we have wind turbines. Right. So I need to thank first my team, so a few postdocs and a few PhD students, which have been founded by, especially by the ERC project, but also by national funding, some Chinese funding, various fundings. Right. So the idea of the project is to look at the acoustic footprint of offshore wind turbines. So both fixed and floating turbines can produce noise, and in particular noise from the flow, from the blades rotating. So this is our acoustic noise that can be propagated through the air and then penetrate into the water, and that can travel long distances from the source and affect marine life. Right. So there are a few studies already in experiment in the sea that have noticed this particularity. And then what we think we are missing is some numerical tools that are able to do so, to check these things. Right. So what do we know? What we know is that for an observer in the ground here, the maximum acoustic amplitude is observed when the blade comes down. So if the blade rotates like this, at roughly 80% of the blade, there is the maximum acoustic production. And this is due to the trailing edge noise, basically, which physically, it's some perturbations that go through the boundary layer, and then these small eddies impinge into the shell layer flow that happens at the trailing edge, and they emanate as acoustic waves, right, that go towards the front. So this means that for a blade coming down, there's waves coming like this, and there's the maximum amplitude happening for a receiver in the ground. So this we know, and from offshore experiments from a while ago. So we can exploit this to try to see what happens in offshore environments. Right, so when we have air and water, what happens is that we have to follow a Snell law. And a Snell law for sound tells us that there's a critical angle of 13 degrees where the sound waves will bounce back from the ocean, and below the 13 degrees, they will penetrate and go underneath the water. So it's not difficult to combine these two ideas, right? So the maximum production of acoustics, and then mask this production of acoustics with a cone, which is defined by this Snell law, and basically filters what's going into the water and what's not. Right, so we can generalize a blade element momentum theory with some acoustic production for each of the sections. We can then calculate the whole acoustic footprint of the turbine, and then mask what's going into the water through this Snell law, taking into account the air-water impedance as well, the difference in media. So if we do so, and we have a general tool, which is not CFD, just a simple tool, let's say. We can calculate for different turbines, so and for farms of turbines, the potential acoustic footprint on the water, right? So here in the work we are trying to publish here, we have used three typical turbines, so 5 megawatt, 10 megawatt, and then a 22 megawatt, which is one of the biggest ones that are proposed these days. And we have calculated the acoustic footprint for one turbine, which will be this guy here. So here you have the noise amplitude against the frequency. And this is for one turbine, and then how it scales when we have farms of 100 turbines, 150 turbines, which is typically what's been installed in the North Sea these days. Right, so what we see is that when we compare that to hearing thresholds, we see that the emissions are clearly above the hearing thresholds, meaning that the animals can indeed hear these turbines. Of course, when we go to larger turbines, the largest ones that are proposed these days, 20 megawatts, those are huge turbines. Only with one turbine, we already see that we're clearly above the hearing threshold. Of course, that scales badly when we have larger farms. Right, so we know this can be a problem. And furthermore, we have recently observed that if we include waves in the ocean, then the 13 degrees angle that was limited just below the turbine can now be found in different regions. And hence we have penetration in other places where initially we didn't have it for a flat sea. Right, so all these tell us that, well, the problem is complicated, but we can already predict some stuff. What we cannot do very properly with this method, with the blade element momentum plus Amiet plus this Snell cone theory, it's really waves, not homogeneous waves. We cannot really do wakes in wind farms, right? Interference between turbines, and it's difficult also to account for the atmospheric turbulence, right? We have some models, but it's a bit difficult. So that tells us that it could be interesting to have a simulation tool, a CFD simulator that can do all this kind of physics, right? And that's the idea of the talk. So the idea is to show you how this general solver Horses 3D that we have developed can be extended to do these wind farms of offshore acoustics at some point. Right, so I will go talk a little bit about horses. I will talk a little bit about the multiphysics with including horses to try to solve this problem. And then a few things on how we can, through machine learning techniques, advance or accelerate or automate these calculations. Right, so what's Horses? Horses is a high order discontinuous Galerkin solver. We have compressible and incompressible versions. We have entropy energy conserving schemes for stability. We can do P or H adaptation. We have explicit and implicit time stepping, but we mainly concentrate these days on explicit. We have various turbulence models, and in particular, we use LES. And during this talk, I will show only Riemann results. And then we can do multi-phase, mesh boundaries, sliding meshes, shocks, plenty of things, but I will focus today on wind turbine stuff. And regarding HPC, we can do CPUs and GPUs recently, so I'll show some results also on the GPU implementation. The solver is open source, so you can download it for free here. There's a paper where we summarize some of the features, which is already quite old. We're preparing now a new one with a GPU version. Right, so in a nutshell, this is the things we can do. We can do turbines, aircraft, multi-phase flows, shocks, such as in here, and of course acoustics, which is of interest for this project as well. And I will try to talk a little bit about a couple of things here. Right, so we use higher order methods. So for those not familiar with higher order methods, or discontinuous Galerkin in particular, the way they work is in lower order methods, in the classic lower order methods, we have a mesh made of triangles, and then we have a piecewise constant value inside each of the elements. This will be finite volumes, right? And then we have to link the solution with fluxes between the elements. In finite elements, you use piecewise linear variations inside the elements. And in higher order methods, you use an arbitrary polynomial inside each of the elements. So this is P1, but we have P2, P3, and we typically use P5, right? To better capture the solution inside of each of these elements. Of course, one can think, why would you increase the polynomial if you can increase the number of elements as opposed to increasing the polynomial? Well, there's two ways, indeed, to get a better solution. One is to add more triangles. The other one is to just increase the polynomial by fixing the number of triangles. Right, so a motivation to do one or the other can be seen here, right? So this is a very simple Poisson equation, elliptic problem, where we plot the accuracy, that's the L2 norm. We know the exact solution, so we can compute the exact error. And we have here the degrees of freedom that we use to solve the system. So this is the degrees of freedom we need to invert the matrix, or to build the matrix, or whatever we do with how to get the solution, right? So what we see here is the colors are different meshes with different number of triangles, and the boxes mean the polynomial order used in each of the simulations. So what we do is H refinement. We increase the number of triangles only. We fix the polynomial. The error of the case only algebraically decreases very slowly, as you can see here. However, if what you do is you fix the mesh to 32 triangles, And what you do is increase the polynomial, 2, 3, 4, 5. The error decreases very fast, right? It's what we call exponential convergence. And this is one of the main advantages of using high polynomials as opposed to low polynomials or low order methods. Right, what this means is that if we want to achieve a particular level of accuracy, 10 to the minus 7, we might as well use a polynomial order 6 on a coarse mesh, because we will require fewer degrees of freedom, that if we were to use polynomial order 2 and on a very fine mesh with a low order method, that will mean using 10 times more degrees of freedom. This relates to how fast we get to the solution, right? Because the degrees of freedom increase the cost, the computational cost to get to the solution. Right, so if we go to a more applied, so that was a very academic case, but my idea is to motivate the use of higher order method for more complicated cases. We can see here in a vortex shedding after a laminar airfoil, you can see that Fluent, which is a low order method with this fine mesh, quickly dissipates the flow structures because of numerical errors, as you see here. However, if we use a higher order method with polynomial order 5 on a coarse mesh, what we see is that the structures are well maintained for a long time, showing that numerical errors are much lower, and then the physics are maintained and not artificially dissipated. Right, so this is already a bit more complicated problem. Now, if you go into acoustics, what's perhaps interesting is acoustics is much more complicated problem, right? So what we need for acoustics is to properly capture what's happening in the boundary layer. So this is all these vortices emanate, traveling through the boundary layer and impinging into the shear flow here, and then emanating sound waves. So for this, we need to well capture what's happening in the boundary layer, what's happening here at the trailing edge, and then how these traveling waves travel towards the observer, which in this case is here. Right, so if we try to do the same exercise for the spectra at this particular point, we increase the polynomial order, and we see a spectra that looks like this. So this is not very promising, right? That doesn't look very good. It does. What we do see though is that for P5, we're getting higher peaks in a region where we think actually the main frequency, tonal frequency, is happening. So this is promising, but we don't see any clear trend. Now, what we can do though, is we can integrate the area below the curve to get an overall sound pressure level. And surprisingly enough, when we do the overall sound pressure level against the degrees of freedom, what we obtain is a curve that looks similar to the very academic case that we showed before, right? So we get exponential convergence, so very rapid decrease of the error when we increase the polynomial order. We see, so this is if we use Fowell and Hawkins to do the propagation. If we do direct propagation, we see a little bit of loss of accuracy, but this is, I think, because of the non-reflecting boundary conditions they were not properly imposed in this particular case. We're rerunning these cases with the right boundary conditions, so you can see some pollution here. But nonetheless, that's much better than low order methods. Now, this is exponential conversion. So what we see is that the error decreases exponentially very quickly, but one would think that the cost will also increase exponentially, and hence there's no advantage whatsoever, right? If the cost was to increase also exponentially, you might as well use a low polynomial. But what we observe when we check for the same case is that the CPU cost in this axis against the degrees of freedom, and now we increase the polynomial, what we see is that the increase in cost is slow and it's almost linear, right? So what we see is an almost linear increase in cost, whilst the error decreases exponentially, meaning it's very advantageous to use higher order polynomials, not only in academic cases like the electric case that I showed at the beginning, but also in practical cases like this one. Right, we have tested our solver horses in many processors up to 10,000, and we see almost ideal scaling for the appropriate meshes and enough polynomial order. And recently we have ported everything to GPUs, and we have checked up to 256 GPUs with 1 billion degrees of freedom. And we see that indeed when we use high polynomials, P5, P7, we get almost ideal scaling. So we're pretty happy with everything. And of course, it's very difficult to compare CPU to GPU implementations. but we have tried to do so. And for example, for this case, which is a typical Taylor-Green vortex case, what we see is that the speed up from going from 100 CPUs to GPUs to one GPU, right? We get 170 roughly times the speed up, right? So it's 270 times faster to run on one GPU. In other words, one GPU it's equivalent to running in 270 CPUs, right? That leads us to very fast or faster iterations per second, per iteration, seconds per iteration, which will lead to, if we have to do an LES simulation with 10 to the 8, for example, time steps, will lead to much faster calculation, right? So we could save 216 days. Right, we have ported that, and I'll tell you what we do exactly to wind turbines. So this now is in compressible solver, multi-phase, and actuator lines. So this is a free surface that moves and you know changes with everything. And here we are seeing a speed up of 245. So I think this very canonical speed up, 270, 275, more or less holds for much more complex implementations, right? So yeah, so that's a little bit about the solver. Let me show you a little bit why these the physics are correctly represented with these formulations that we have. So first, how we simulate wind turbines, and then I'll go into the acoustics just later. So there's many ways to simulate wind turbines in CFD. The simplest one is actuator disk. Then there's actuator lines, which is the one I'm going to present today. We have tried also in mesh boundaries, and we are currently developing sliding meshes as well. Right, but I would concentrate on actuator lines because it's good enough to get some acoustics. So let me just show you. Right, so what's an actuator line? Actuator line is a source term that we add into the Navier-Stokes equation that represents the blades by individual forcings along the span. And this can be rotated, so we get some movement and some changes in azimuth. We need some tabulated data to do so. So we get CL and CD values from other sources, for example, XFoil. And then we have to blend this function not to get a sudden peak in the solution. So we smear that, taking into account the mesh and the polynomial order, etc., through a Gaussian that smears a little bit the individual force. Right, so if we run these simulations, what we see is that indeed the blades are rotating. That's okay. And what happens with the accuracy, that's the interesting part. So of course, since we can change the polynomial, we check what happens with the polynomial. So P2 will be this very smeared surface of the vortex. But when we increase the polynomial to reasonable values, P7, we get the right physics with the clear distinct tip vortex here. So this is with no tower or nacelle. This is just the blades rotating. And what's interesting with these cases is that you can get a clear tip vortex, which eventually transitions to turbulence, and then you get a much more mixing. And this is actually a way to check the accuracy of the results. The longest these tip are maintained, the less numerical errors are in the simulation. This is something that people check typically. Right, so what we have done is comparing our P7 solution, which uses 37 million degrees of freedom, against an open foam solution with 100 million degrees of freedom. And what we see is that, well, overall the flow looks similar, but our simulations maintain the tip vortex without transitioning to turbulence for longer than open foam, suggesting that our errors are smaller than the open foam with 3 times more degrees of freedom, which is, again, reminiscent of what we talked about at the beginning with the elliptic problem, the very simple elliptic problem, where exponential, so using a higher order polynomial, makes the error decrease much faster. Right? And this is what you can see here. Again, for a much more complex problem. Now, if we now include the tower and the nacelle, and we compare that to the experiments, we see that we get quite good agreement with the experiments at different diameters downstream of the turbines. You can see here Of course, if we don't include the nacelle and the tower, that's the blue line, we don't get good agreement. But once we include it, everything is fine. Right, the next step is to include atmospheric boundary layers, so turbulence in the inflow. And what we see for the flow is that if we use low turbulence levels, the wake is maintained for longer and it dissipates much faster when we include high turbulence levels, right? And this can be important also for the acoustics that I'll show you quickly later. So this is a precursor simulation. We generate the turbulence and then we input it in the simulation with the turbine. Right, let's talk about the acoustics. So as I mentioned, we can get some noise because we have some frequency happening in these rotating blades. And indeed, if we check the dilation field, for example, we can see some indeed waves with low frequency emanating from the turbine. But of course, we don't have the whole physics there. We don't have the blades really, right? What we have is some things that are rotating. So we get these very low frequency acoustics happening and emanating and propagating, but we don't get the high frequency content due to trailing edge noise. So what we do typically is we include the missing scales or the missing acoustics that we compute with Amiet, which is a method to compute sections, airfoil sections and the acoustics from this, so the trailing edge noise. And we can include that into the solver as missing sources, and then we can compute the overall spectra. And if we do so, what we get is quite good agreement with experiments in field, where we are able for a whole wind turbine to reproduce the acoustics. Right, so we can also check the propagation and how the wake, for example, of the turbine affects the propagation, which is not always taken into account in simple acoustic solvers for wind turbines. And what we see is that there's various effects that the wake can have. So for example, if we don't include the tower in the calculation of the wake, this flow is very different, right? And then what we see is that the acoustics are also very different. So if we don't include the tower, we have these acoustics. If we include the tower, we get a higher noise, higher amplitude of the noise going towards the ground here. So the acoustics are going down. So the pressure waves are going down, meaning that we have a high amplitude level here, right? And that can be important if what we are studying is the acoustics downstream, right? But we will miss this completely if we didn't include the tower in the calculations. Again, similarly, if we don't include the turbulence, atmospheric boundary layers, what we get is an acoustic at the same location, this one, which will be lower than when we include the atmospheric boundary layer, right? So taking into account the geometry and the precursor simulation to generate the turbulence levels, it's very important to try to get the right acoustics. Right, so that's wind turbines in general. Let's now go into the offshore turbines. So if we want to simulate offshore turbines with the multi-phase solver, and we've developed during the last 5-6 years a multi-phase solver, but it's not the typical one. So normally you will use volume of fluid. I think that's the most famous multi-phase solver or implementation. What we use is a phase field model, right? So phase field model, what assumes is that the interface is not sharp. It's not a sharp interface, but it's a diffuse interface, right? So diffuse interface, basically the solution of the equations we're going to solve is a hyperbolic tangent, meaning that the solution is smooth enough such that we can get derivatives and everything. And that means that we can apply this easily to higher order methods. So higher order methods don't like sharp interfaces or sudden shocks or sudden changes, because then you get Gibbs phenomena and you get oscillations. Here we don't have this. We have a diffuse interface, so a smooth interface, and hence we can do polynomial adaptation or any kind of higher order tricks without losing exponential conversion, without losing the nice properties of our higher order methods, right? So if we want to do this for multi-phase, what we do is we solve the Navier-Stokes equations, and in addition, we solve the Cahn-Hilliard equation, which governs the concentration of the fluid concentration, right? So we need to solve these additional equations. Maybe not easy to solve, but it's feasible. So we have tested that with very simple problems. So this is the classic test problems that you do to check accuracy and everything. We have also tried local adaptation for dam break. So this is only at the interface. We are adding polynomial to capture really the features at the interface. And perhaps more interestingly is that this formulation, it's not the standard formulation of the Navier-Stokes with Canhillier, but it's an energy stable formulation, right? That means that if you were to run these cases with a normal formulation of incompressible Navier-Stokes plus Canhillier, eventually your solver might blow up. It might run for a while, but then if the interface starts showing some oscillations or some high frequency features, then the solver might blow up and then you end up without any result. Now, if what you do is you use a an entropy or energy conserving formulation, what you are forcing the solver to do is to solve. So what you're doing is not allowing the solver to build up energy or entropy in a non-realistic way. And this prevents the solver from blowing up, right? And with this, we get stable solutions that can last till the end. How do you do this? In 2 words, you have the Navier-Stokes equation. Once you discretize the Navier-Stokes equations, what you get is a discrete system of equations. And what happens is that if you are into the continuous level, the original level, you can check that kinetic energy or entropy are indeed maintained, right? So this is in the continuous level, everything is maintained. You can write an equation for the kinetic energy, and everything should be set and maintained. Now, when we discretize the equations, often, if we are not careful, the discrete version of the equations will not maintain the discrete version of the kinetic energy or the discrete version of the entropy equation. This will be violated by some things that in the process happened when we did the numerics. So what we do in these cases is we check that our discrete version of the Navier-Stokes equation also fulfill the discrete version of the kinetic energy and or the discrete version of the entropy equation. We do that on the paper. We don't solve additional equations on the solver, but we make sure that the discretization we did, it's properly done such that we don't violate these conservations of energy or entropy, right? So then the underlying method has a transport equation for energy, and hence everything gets transported and balanced, and things cannot blow up and accumulate energy unrealistically, let's say. So this is what our solver does. And then what we see is that for smooth interfaces, we see very similar behavior with when we use standard DG or split forms or these energy stable schemes. But once we start having oscillations and errors, inaccuracies, or aliasing really at the interface, what we see is that the higher the energy stable formulation, it's much more stable, right? And finishes the computation, whilst the other one was just blowing away. Right, so this is what we use to then solve actuator lines with multi-phase flows, right? So we don't lose this energy stability or entropy stability, and we can solve everything together to get this kind of flows. This is a top view of this particular thing. This is a side view of the wind turbine. Right, so what we're doing these days is adding waves to the simulation. So we can now have waves, and then we can see the effect of the waves on the wind turbines. And what I think it's very important though, in what we are doing with this framework of the multiphase, is that this framework allows for generating a pressure wave in the air, and we can check that the penetration is correct, right? And we get the right wave length in the water and in the air, and everything is physically correct, right? We get some bouncing back, we get some transmission, but everything is correct. So we have checked that for some cases that we have tried. And what we see, so for example, that's a change in media of some particular width. So this is our interface width, which is not sharp. It's a small value for the interface. We throw a wave and we check what's transmitted, what's not. And what we see is we're able to check that the errors decay exponentially. So this is, again, the same nice feature of how the methods that we had in the very canonical test problem at the beginning that now we can observe in this much more complex problem. And we have checked that also for Snell's law. So then we have an angle of, we throw a wave with an angle, and then we can see that the errors are bounded for any of the angles, right? So near the limit, 13, for air and water, we get almost the same error as for lower angles, right? So there's no huge increase when we get to the limit critical angle. So we're quite happy with this. This is almost accepted, I will say, at JCB. Right, so this is the physics. So you might tell me, okay, where is the turbine with acoustics, with everything coupled together? And the answer is not yet. Okay, we're almost there. We have all the ingredients, I think, but I don't have yet the spectra for everything on the water, but that's happening soon. Now, of course, there's the idea of accuracy and automation, how we can do this. And for this, we use reinforcement learning. So if you're not familiar with reinforcement learning, this is the tool, the algorithms that are used to play Atari or to play Go or chess, such that the machines can win at these games. And it's an agent that interacts with the environment through some actions and gets rewards if it does it well, or the rewards can be negative, penalizations. And through the interaction with the environment, he can learn what to do. Right, so what we have done is use reinforcement learning to locally adapt the mesh. So this is in each of the elements, we can check the accuracy necessary, and then the reinforcement learning will anisotropically, so in each of the directions, will choose the polynomial that it's more adequate in this case. So the reinforcement learning does, all the training happens offline, right? And then when we deploy, it's just a lookup table thing. So it's very not expensive. So everything happens in this paper here, where we have solutions for various cases. And in particular, we have also included for wind turbines. So you can see here the wake is developing, and the reinforcement learning agent, it's enriching the polynomials. So it's making it larger in this figure, but it's enriching the polynomials in the wake. We also, just to give you more ideas, we're also using reinforcement learning for wind turbine control. So we have a couple of papers on this. And here you can see clearly the idea of the RL, the reinforcement learning. So here what we're doing is changing the pitch, the rotor speed, or the yaw angle to extract more energy from the flow when we use wind turbines. So what happens here is, as time evolves, at the beginning, the reward is negative. So basically the RL is trying a lot of things, but it's not doing it right. But eventually, it learns what it has to do, and then the rewards are all positive, right? And from that point onwards, when he knows what he has to do, it extracts all the energy, all the possibility. This is in training, which we typically do with simple winds. So they might be constant winds with different angles, etc., different velocities, but he learned what to do for simple winds. And then when we validate, when we do the deployment, what we do is we throw some turbulent real winds to it. And then we check what happens if we were to use a PID controller, a classic PID, or we try different algorithms for RL. We use a DQN algorithm, and then what we see is that we can extract much more energy than with simple PID methods. We have also generalized that for energy and acoustics. And here what we see, so now we get some rewards that are the link that the power and the acoustics produce. And what we see is that we get with the quiet against the power, it's let's just maximize power, while it's try to maximize power whilst getting the acoustics, limited. So we get some sacrifices in the power for sometimes, but when we look at the acoustics, it's because it's doing something to limit the acoustics below this threshold that we have set. And well, we lose a little bit of power, but not too much, whilst we are good with the acoustics. This is what the algorithm can do. And now we're extending this to multiple turbines, where we have one turbine behind the other one, and we can try to use RL to maximize power whilst minimizing acoustics. So we have some preliminary results, but I will not bother you with that. And I'll finish with something that we are writing these days, which is a very simple idea. And if you recap from the very beginning of the presentation, we were talking about the maximum acoustics being produced here for an observer in the ground, etc., and the Snell cone. So one thing that it's not too difficult to do is to try to pitch the blades when we are in this region. So if we know here's the maximum acoustics that are going to go underwater, let's try to minimize the produced acoustics in this region, right? So for this region here, we will pitch the blades such that we produce less acoustics. We have done so, and the paper is under review these days. And the idea of this is we don't sacrifice as much energy as if we were to change everything all the time. We just lose a little bit of energy in this region where we are minimizing the acoustics. Right, so with this I will finish. Some conclusion. I think noise from wind turbines can affect marine life. There's indications that this can be a problem in the near future. But there's no tools or experiments to predict this footprint. I think we are trying to develop the first kind of set of tools that can do this. We have a higher order solver that is roughly well developed, which is enhanced with AI. And in the next few months, I think we will be able to, generalize footprints for offshore turbines, really. And of course, the next step is for farms. So I think with this, I'll conclude.